Fresh paint is the cheapest way to hide a death sentence. You look at a restored part and see a budget saved. It looks back at you, waiting for the moment of peak stress. We will analyze 6 stories where a cosmetic repair concealed the fatal decay within. This isn't about luck. It's about the cold calculus of physics, which always wins against greed. Be careful. Old parts have long memories. Be wise when buying scrap. On the humid morning of July 14, 2011, in a heavy vehicle repair shop in Ohio, the air was thick with the smell of diesel, grease, and the stagnant heat of midsummer, a sensory baseline that defined the working life of mechanic Donnie Wilson. He was a man who understood the language of heavy machinery, a veteran of the trade who had spent years wrestling with the stubborn bolts and immense weights of industrial transport. But familiarity is often the precursor to a fatal oversight. On this particular day, the task at hand was a tire change on a commercial truck, a routine procedure that hides a lethal amount of potential energy behind the mundane hiss of an air hose. The specific component involved was a multi-piece wheel assembly, known in the industry by the grim and earned nickname, the widowmaker, a design that relies on a separate, removable steel locking ring to hold the tire onto the rim base. Engineering standards dictate that these rings must be pristine, free of deformation and rust, because they are the only barrier between the technician and a catastrophic release of pressure. Yet the economic reality of a repair shop often clashes with the strict laws of physics. Instead of ordering a factory-new locking ring, which would cost money and delay the job, the decision was made to reuse an old weathered component salvaged from the scrap pile. To the naked eye, the ring looked solid enough, a circle of heavy iron that had survived years of road salt and friction. But at the microscopic level, the metal was compromised. Deep-set corrosion had eaten away the precise geometry of the locking lip, and fatigue had robbed the steel of its elasticity, turning it into a dormant grenade waiting for the pin to be pulled. Donnie cleaned the part, perhaps brushing off the surface rust, and seated it into the rim's gutter, trusting the visual appearance of the steel over the invisible reality of structural decay. He began the inflation process, listening to the rhythmic chug of the compressor as it pumped air into the tire, slowly building the internal pressure to a standard 100 psi. In the mind of a layman, air is weightless and harmless, but under compression, it behaves like a compressed spring of immense power. At 100 psi, the air inside a large truck tire exerts over 40,000 pounds of total force against the rim structure. As the gauge needle climbed, 60, 80, 90 psi, the tire sidewalls pushed outward with the strength of a hydraulic press, testing every millimeter of the old locking ring's grip. The corroded metal, weakened by years of exposure to the elements, began to surrender, shifting imperceptibly in its groove as the forces exceeded its degraded load-bearing capacity. Donnie was standing in the trajectory zone, the cone of danger directly in front of the wheel assembly, likely checking the bead seating or preparing to disconnect the line, unaware that the physics of the situation had already decided the outcome. The failure was not a slow leak, it was an instantaneous, explosive separation. The locking ring, unable to withstand the final pounds of pressure, yielded to the stress and was ejected from the rim with the velocity of a cannonball. The stored pneumatic energy released in a split second, propelling the heavy steel ring outward at supersonic speed, transforming a piece of scrap metal into a kinetic projectile capable of severing concrete. The physics of the impact were absolute and merciless. The ring struck Donnie Wilson in the upper torso and neck region with a force that the human body is simply not designed to withstand. There was no opportunity for a reflex action, no time to flinch, and no moment of realization. The transfer of energy was faster than the speed of neural processing. The blunt force trauma was catastrophic, causing immediate and non-survivable massive internal trauma before his body even hit the workshop floor. The sound of the explosion echoed like a gunshot through the facility, followed immediately by the deafening, high-pitched scream of the remaining air rushing out of the tire, a violent exhale that marked the end of the event. When silence finally returned to the garage, the scene was a frozen tableau of industrial cause and effect. The tire lay flat and harmless. The air compressor continued its mindless cycle. and the reused locking ring lay at rest, its structural failure now visible to anyone who cared to look. The tragedy of Donnie Wilson serves as a brutal forensic lesson in the cost of economy. The decision to save a small sum on a replacement part had incurred the maximum possible penalty. In the cold calculus of engineering, rust is not just a cosmetic blemish, but a cancer of the metal that erases the margin of safety. And when that margin is gone, gravity and pressure always collect their due. The widowmaker had lived up to its name, proving that while a mechanic can negotiate with a customer on price, he can never negotiate with the immutable laws of pressure dynamics. In the rural expanse of Missouri, sometime in 2014, the heavy clay-rich soil created a scenario that is familiar to anyone who works the land. A vehicle trapped in the grip of suction, where the friction of the mud overpowers the traction of the tires. For Chad Wall, this was a problem that required a mechanical solution, a routine application of horsepower and leverage that plays out in fields and back roads every day. The tool chosen for the extraction was a nylon towing strap, a ubiquitous piece of equipment found in the bed of almost every work truck, often kept for years, exposed to sunlight, moisture, and the abrasion of previous jobs. In the economy of rural repair and recovery, a strap is considered good as long as it isn't snapped in two, but this visual assessment ignores the microscopic reality of polymer degradation. The strap Chad utilized was tipped with a heavy, drop-forged steel hook, a dense piece of industrial metal designed to latch onto a frame rail or bumper. To the casual observer, the hook represents security, a solid connection point. But in the physics of recovery, a metal hook at the end of a nylon strap is a dormant projectile. Unlike a steel chain, which is static and transmits force directly, a nylon recovery strap is dynamic. It is designed to stretch by up to 20% of its length. This elasticity is a feature, not a bug, allowing the strap to store kinetic energy like a massive rubber band to help snatch a stuck vehicle free. However, when an old, weathered strap is used, one where the fibers have been stiffened by UV exposure and weakened by internal friction, that energy storage mechanism becomes a lethal trap. As the recovery vehicle began to accelerate, the engine roared against the resistance of the stuck load, and the strap pulled taut, vibrating with the immense tension of the pull. The mud was refusing to let go, acting as a powerful anchor, forcing the nylon to stretch further and further, loading it with thousands of foot-pounds of potential energy. Chad was positioned in the driver's seat of the pulling vehicle, separated from the straining line only by his rear windshield, a sheet of tempered safety glass designed to withstand road debris, not concentrated ballistic impacts. As the tension peaked, the system reached its critical failure point. It is unclear whether the strap snapped due to fiber exhaustion or if the hook slipped from its mounting point due to the angle. But the result was dictated by the violent laws of elasticity. The failure was instantaneous. The stored kinetic energy, having nowhere else to go, was released in a millisecond, causing the strap to recoil toward the source of the pull with the velocity of a cracked whip. The heavy steel hook, suddenly liberated from the load, became a missile. This phenomenon, known in the industry as the slingshot effect, accelerated the multi-pound chunk of iron to speeds exceeding 100 miles per hour in the blink of an eye. The human brain processes visual information in roughly 13 milliseconds, but the hook was moving faster than the speed of perception. It struck the rear windshield of Chad's truck with such focused kinetic energy that the glass offered no meaningful resistance. It didn't just shatter, it allowed the projectile to pass through with its momentum virtually unchecked. The hook continued its trajectory into the cab, striking Chad Wall in the back of the head. The impact was not merely a collision, it was a transfer of massive concussive force into a localized area. The trauma was blunt, catastrophic, and immediately fatal. There was no moment of pain, no realization of the error, and no time to react. The physics of the event resulted in an instantaneous, fatal conclusion. 1 second, there was the loud, straining noise of the engine and the focus on the recovery. The next, there was only the idling motor and the silence of a job that would never be finished. The tragedy of Chad Wall is a brutal forensic reminder of why modern safety protocols strictly forbid the use of metal hooks on kinetic recovery straps. The reused aging equipment, which had likely performed this exact task a dozen times before without issue, finally encountered the specific set of variables required to turn a tool into a weapon. In the aftermath, the strap lay limp in the mud, its energy spent, leaving behind a scene that looked less like a workplace accident and more like the result of a targeted, high-velocity impact. The old reliable part had failed in the worst possible way, proving that in the equation of force, mass, and elasticity, the weakest link always dictates the survival rate, proving that elasticity, when it fails, offers the most violent and immediate form of payback. On the humid evening of July 26, 2017, the Ohio State Fair in Columbus was a vibrating landscape of neon lights, sugar, and the collective scream of thrill seekers, a sensory overload designed to make you forget about the boring laws of reality. Among the thousands of people seeking an adrenaline rush was 18-year-old Tyler Jarrell, a young man who had just committed his future to the service of his country by enlisting in the United States Marine Corps only days prior. He stood in line for the Fireball, a mechanical giant known technically as the KMG Afterburner, a ride that had been a staple of the fair circuit for nearly 2 decades. The machine is a masterpiece of kinetic intimidation, a massive pendulum arm that swings 120 degrees into the sky while simultaneously spinning a circular gondola of passengers at a dizzying 13 revolutions per minute. To the casual observer, and indeed to Tyler, the ride looked like a monument to modern engineering safety. Its steel arms gleamed under the floodlights, the yellow and orange paint was fresh, and the inspection stickers were current. However, this cosmetic perfection was a lethal facade that concealed a rot deep within the machine's skeleton. The ride was not new. It was an 18-year-old veteran of the road, a collection of steel components that had been assembled, disassembled, and transported across continents, exposed to years of rain, condensation, and outdoor storage. The specific component that held Tyler's fate was the gondola support beam, a hollow steel member designed to carry the dynamic load of the passengers. In the world of structural engineering, a hollow tube is efficient and strong, but if it is not perfectly sealed, it becomes a moisture trap. For years, water had silently pooled inside the bottom curve of the support arm, creating an invisible chemical reactor that no one bothered to check with advanced tools. While the exterior was sandblasted, primed, and painted to look factory new, a classic case of restoring an old part rather than verifying its structural integrity, the interior was being eaten alive by oxidation. The steel walls of the beam, originally manufactured to be several millimeters thick to withstand multiple Gs of force, had been reduced by rust to the thickness of a piece of cardboard. The metal was experiencing advanced structural decay from the inside out, a dead component masquerading as a living machine. The operators and inspectors, trusting the visual condition of the exterior paint, had no idea they were strapping passengers into a structure that was chemically compromised. As the ride cycle began, the pendulum started its rhythmic swing, pushing the passengers higher and higher into the summer night. The physics of the afterburner rely on the seamless transfer of centripetal force and gravity. As the arm swings through the bottom of the arc, the G-forces spike, putting maximum tension on the steel connection points. Tyler Jarrell was seated in the gondola, experiencing the rush of acceleration, unaware that the metal holding him was groaning under the strain. The old part was holding on by a thread of oxidized iron. As the ride reached its operational peak, swinging past the vertical axis with the full weight of 24 passengers, the structural integrity of the sweep arm evaporated. It did not bend, it snapped. The sound was a sharp, sickening crack of shearing metal that cut through the noise of the carnival music. The corroded steel, no longer able to support the dynamic load, separated completely from the main hub. The gondola, now a free-flying projectile, was liberated from the pendulum's arc but retained all its kinetic energy. It slammed into the metal structural deck of the ride with the violence of a high-speed car crash. The impact was catastrophic. The carriage broke apart, leading to the sudden ejection of the occupants as the carriage disintegrated. The resulting high-velocity impact was immediately fatal, leaving no room for medical intervention. The forensic analysis that followed revealed the terrifying truth of the restoration. The beam's interior was filled with a slurry of rust and water, the steel wasted away to almost nothing. The fresh paint on the outside had acted as a structural shroud, hiding the rot until the moment of peak stress. This was not a freak accident. It was the inevitable result of treating an aging, fatigued mechanical component as good enough based on surface appearance. The tragedy of the fireball is a grim lesson in the deception of maintenance. A coat of paint can hide 1,000 sins, but it cannot hold back the laws of physics. Tyler Jarrell's life was exchanged for the cost of a proper ultrasonic inspection, proving that in the ruthless arithmetic of heavy machinery, what you cannot see is often far more deadly than what you can, and an old part is only safe until the rust decides it is time to let go. The ride, the lights, and the music stopped, leaving only the silence of a fairground that had suddenly become a crime scene, and the broken beam lay on the deck, its hollow, rusted core finally exposed to the world, a testament to the lethal cost of ignoring the slow, quiet decay of time. On the bright, quiet afternoon of May 15, 2009, in the rural expanse of Queensland, Australia, the dangerous allure of making do with what you have collided with the unforgiving laws of metallurgy in the backyard workshop of Stephen Jervis. Stephen was a man who embodied the spirit of the self-reliant mechanic, a builder who saw potential in scrap piles and believed that heavy iron was always better than modern plastic. He was in the final stages of constructing a homemade log splitter, a powerful hydraulic machine designed to take the brutal labor out of preparing firewood for the winter season. The heart of this machine was a new stationary petrol engine, a modern unit capable of high rotational speeds, but the transmission system required a pulley to transfer that power to the hydraulic pump. Instead of purchasing a new rated steel pulley, Stephen turned to his collection of vintage agricultural salvage and retrieved a massive cast iron pulley that had once belonged to a tractor from the 1950s. To the naked eye, this component was a masterpiece of old-world durability, heavy, thick, and seemingly indestructible, having survived half a century of farm work without a scratch. However, this visual solidity masked a critical flaw in the material's application. Cast iron is a material defined by its rigidity. It has immense compressive strength, meaning it can support the weight of a building, but it has almost zero tensile elasticity. Unlike mild steel, which will stretch or deform before it breaks, cast iron is brittle. It does not give, it shatters. Furthermore, this specific pulley was designed for the slow, thumping rhythm of a vintage tractor engine, likely rated for a maximum of 540 to 800 revolutions per minute. Stephen mounted this relic onto the shaft of his modern engine, which was capable of spinning at speeds exceeding 3,000 RPM. He had unknowingly created a kinetic mismatch of fatal proportions. As he finished the assembly and prepared for the test run, the workshop was filled with the anticipation of a job well done. He started the engine. The piston fired, the shaft turned, and the heavy iron wheel began to blur. At idle speed, everything appeared normal. The belt hummed, and the heavy flywheel effect of the pulley made the engine run smooth. But as Stephen opened the throttle to generate the hydraulic pressure needed to split logs, the physics of rotation began to wage a silent war against the molecular bonds of the iron. This is the domain of hoop stress, the force that pulls a spinning object apart from the inside out. As the engine RPM climbed past 1,000, then 2,000, the centrifugal force acting on the rim of the pulley didn't just double, it quadrupled. The outer edge of the wheel was trying to travel in a straight line, held back only by the crystalline structure of the aged iron. Deep inside the casting, invisible microfractures, accumulated over 50 years of heating, cooling, and rust, began to propagate at the speed of sound. The iron was groaning at a frequency too high for the human ear to register, vibrating with the tension of being spun at nearly 4 times its design limit. Stephen stood next to the machine, likely leaning in to check the pump alignment or the belt tension, his body positioned directly in the plane of rotation. He trusted the weight of the part, believing that its mass equaled safety, not realizing that he was standing next to a loaded fragmentation mine. The failure point arrived without a warning wobble or a screech. It was instantaneous. The tensile strength of the iron was finally exceeded by the centrifugal load, and the molecular lattice snapped. The pulley did not just crack. It experienced explosive structural disassembly. In a fraction of a second, the solid wheel transformed into 3 jagged sectors of heavy shrapnel, each weighing several pounds, launching outward at the tangential velocity of the rim, hundreds of miles per hour. One of these massive iron shards was released directly towards Stephen's midsection. The physics of the impact were devastating and absolute. The fragment struck him in the abdomen with massive, unstoppable kinetic energy. The human body, composed of soft tissue and fluid, offers zero resistance to jagged cast iron moving at ballistic speeds. The trauma was blunt, penetrating, and immediately catastrophic, causing massive disruption to the internal organs and major vascular structures. There was no time for adrenaline to mask the shock, no time to shut the machine down, and no time to regret the economy of using the old part. The impact was so severe that it caused immediate incapacitation. The engine continued to run, the shaft now spinning a jagged, unbalanced remnant of the hub, while the silence of the aftermath descended over the shed. The tragedy of Stephen Jervis is a brutal, forensic lesson in the limitations of material application. He died because he treated a flywheel as a simple part, ignoring the fact that every rotating object has a speed limit dictated by its diameter and its material composition. The solid iron from the 1950s was never designed for the high-speed violence of the 21st century. In his attempt to build a tool for survival using scrap, he had inadvertently constructed a weapon that obeyed the cold, mathematical laws of rotation, proving that while ingenuity can solve many problems, it cannot negotiate with the structural limits of cast iron. In the sun-drenched suburbs of California, amidst the endless sprawl of home workshops and weekend projects, the events of 2018 surrounding Hani Albana serve as a grim testament to the hidden shelf life of industrial materials. Hani was a man who took pride in his hands, a capable and experienced individual who understood the mechanics of repair and the satisfaction of a job done personally, yet his competence could not save him from a danger that was chemical, not mechanical. The setting was his own garage, a sanctuary of tools and potential, where he was preparing to perform a routine metal-cutting task using an angle grinder. This tool is a staple of the modern workshop, a compact electric motor that spins a disc at terrifying speeds to slice through steel, but it is also one of the most unforgiving instruments in existence. The specific task required a fresh, abrasive cutting wheel, a consumable item that wears down with use. Rather than pausing his work to drive to the hardware store, a delay that frustrates any focused craftsman, Hani searched his inventory and found an old unused disc. It had been stored for years in a basement environment, likely subjected to the fluctuating humidity and temperature cycles that define the passage of time. To the naked eye, the disc appeared pristine. It was the correct diameter, the label was intact, and it showed no cracks or chips. However, this visual inspection failed to detect the microscopic rot within. An abrasive cutting disc is not a solid piece of stone. It is a composite structure, a mixture of hard grit, like aluminum oxide, held together by a binder, typically a phenolic resin. This resin is organic, and like all organic compounds, it has a finite lifespan. Crucially, it is hygroscopic, meaning it slowly absorbs moisture from the air. For years, as that disc sat in the damp darkness of the storage area, the water vapor in the air was silently attacking the chemical bonds of the glue, softening the matrix that was designed to hold the abrasive grains together against the violence of rotation. Hani unknowingly picked up a dead component, a structural failure waiting for a trigger. He mounted the disc onto the grinder's spindle, tightened the locking nut with the wrench, and prepared to make his cut. He was not acting recklessly. He was simply following the logic of economy, reusing a part that looked new. When he depressed the paddle switch, the electric motor surged to life, instantly delivering torque to the shaft. A standard 4.5-inch angle grinder operates at approximately 11,000 revolutions per minute. At this velocity, the outer edge of the disc is traveling at roughly 180 miles per hour. The physics inside the disc transformed into a violent, invisible tug-of-war. The centrifugal force was pulling the abrasive mass outward with thousands of pounds of tension, creating a phenomenon known as hoop stress, while the degraded, moisture-compromised resin was struggling to maintain the disc's integrity. The old part was being asked to sustain G-forces it was no longer chemically capable of handling. Hani leaned over the workpiece, positioning himself to see the cut line, a common posture that unfortunately placed his upper body directly in the plane of rotation, the specific geometric line where a detached fragment would travel. The failure did not happen gradually. There was no warning vibration, no wobble to signal the danger. It occurred in less than a single rotation. The resin bond, exhausted by age and humidity, simply surrendered. The disc disintegrated explosively. The centrifugal force, no longer restrained by the binder, converted instantly into linear kinetic energy. A large, jagged sector of the ceramic and fiberglass matrix broke free from the hub and was launched tangentially. It became a razor-sharp projectile moving at the speed of a bullet. The shard struck Hani Albana in the chest with devastating precision. The physics of the impact were overwhelming. The ceramic material, harder than bone and moving at ballistic velocity, bypassed the natural protection of the rib cage. The trauma was penetrating and immediate, causing catastrophic trauma to the chest cavity. The event was so fast that the human nervous system likely could not process the pain signal before the systemic collapse of circulation occurred. One moment, there was the high-pitched whine of the electric motor and the focus on the task. The next, there was the silence of a life cut short by a piece of equipment that cost less than a few dollars. The tragedy of Hani Albana is a haunting, forensic reminder of why manufacturers stamp expiration dates on the metal rings of cutting discs. A warning almost everyone ignores. The fatal outcome was caused by him treating a chemical composite like a permanent tool. Unaware that the invisible decay of the bonding agents had turned a useful object into a fragmentation grenade. The old part from the basement had saved him a trip to the store, but it extracted a price that no amount of efficiency could justify, leaving the spinning tool on the floor as a grim testament to the fact that in the battle between degraded resin and 11,000 RPM, the laws of physics are absolute and offer no mercy to the unaware. On August 24, 2011, the Robinson R-44 helicopter piloted by Philip Jones was a machine held in the sky by a simple, brutal principle: the perfect rotation of two main rotor blades. To a pilot, the rhythmic beat of these blades is the sound of life itself, a constant reassurance that the laws of physics are being correctly managed. The entire aircraft and the life within it hangs from these two slender airfoils spinning at over 400 revolutions per minute. There is no backup system. If the blades fail, the flight is over. The tragedy that befell Philip Jones began not in the air, but in a transaction, a decision driven by the immense cost of aviation maintenance. The main rotor blades on his helicopter were not factory new. They had been purchased as used components to reduce operational expenses. However, their history was far more sinister than simple secondhand status. The blades were, in fact, scrap metal, salvaged from a previous helicopter that had been involved in an accident. Somewhere in an uncertified workshop, an unknown technician had performed a purely cosmetic restoration on these critically damaged parts. The dents were filled with automotive body putty, the surface was sanded smooth, and a fresh coat of paint was applied to create the illusion of airworthiness. This act of deception concealed a fatal, invisible flaw deep within the blade's internal structure: delamination. A helicopter blade is not a solid piece of metal. It is a bonded assembly, typically consisting of a main metal spar that acts as the bone, with a thin aluminum skin glued to it. Delamination is when that bond fails and the skin begins to separate from the spar, creating an internal air pocket or bubble. This separation catastrophically weakens the airfoil, turning a precisely engineered flight surface into a ticking time bomb. As Philip Jones flew, the blades were under immense aerodynamic load, flexing and twisting with each rotation, fighting against air resistance and the force of lift. The delaminated section, a hidden wound covered by paint, began to peel back further under the stress of flight. The initial sign of the failure would have been a sudden, violent and uncontrollable vibration that shook the entire airframe with the force of an explosion. The helicopter, once a stable and responsive platform, would have instantly become a bucking, unmanageable beast. Jones, a skilled pilot, would have recognized the severity of the situation in a fraction of a second, but there was nothing he could do. The failure was not in a system he could shut down or bypass. It was in the very wings that gave him flight. The delaminated blade skin likely peeled back or separated completely, instantly destroying the aerodynamic balance of the rotor disc. This created a massive imbalance, causing the helicopter to enter an unrecoverable tumble. No longer flying but falling out of the sky. The loss of controlled lift was immediate. The final moments of the flight were a blur of chaotic physics, a descent governed by gravity, not by the skill of the pilot. The impact with the ground was at a velocity that made the structural limits of the airframe and the occupant irrelevant. The forces involved were absolute and non-survivable. In the aftermath, accident investigators sifting through the wreckage would have found the smoking gun, the failed rotor blade. When they scraped away the fresh paint, they would have discovered the cheap body filler, the sanded down damage from a previous life, and the clear evidence of the delamination that initiated the disaster. The restored old part, which had been purchased to save a few $1,000s, had betrayed the pilot in the most lethal way possible. The crash of Philip Jones's R-44 is a chilling forensic case study in the danger of uncertified parts in aviation. It proves that a coat of paint can be the most effective camouflage for a fatal injury in a machine, hiding the truth until the moment of maximum stress. In the cold, unforgiving environment of the sky, there is no margin for error, and the integrity of a part cannot be judged by its surface appearance, because the laws of aerodynamics will always expose the weakest link. In each of these cases, someone decided that old was good enough. Who is more at fault? The person who bought the junk or the one who agreed to work with it? If you were a juror in the Fireball Ride case, would you demand a life sentence or just a fine? Deliver your verdict in the comments. Subscribe to the channel so you don't miss the next autopsy of reality. Your like is your vote.